Okay, last time we ended with the breakdown of a Michael reaction. A Michael product is a 1,5-dicarbonyl, and to do this breakdown, you break the 2,3 bond carbon 2 gets a hydrogen, carbons 3 and 4 get a pi bond. So if you wanted to do the Michael reaction in earnest, this molecule right here is the one we want to be the nucleophile, because that's the one with carbon 2. That's the one that received the H in the breakdown. We can treat that molecule with LDA, give an enolate, and then we treat that enolate with a molecule referred to as a Michael acceptor. What a Michael acceptor essentially is an alkene, or in some cases an alkyne. The most important part is a pi bond attached to a carbon attached to an electron withdrawing group. We'll get to why that's important that it's be an electron withdrawing group in just a moment. But essentially what we're doing is, in this next step, is we're going to create a bond between carbons 2 and carbon 3. So here's 1, 2, 3, 4, 5. So these electrons swing down, kick these electrons over to carbon 3. These electrons go here, these electrons go here. Now, go ahead and pause the video and draw the products of this reaction right here. Personally, what I have to do when I do these is I have to number. One becomes a double bond O. 2, 3 get the new bond. 4, 5 we get the pi bond there. The electrons go up, and then there's this methyl group attached to 5. And then, to finish up the reaction, you add a proton source. And that proton source is there to protonate the resulting enolate. So to kind of recap this reaction, we used a strong base to deprotonate, added in a Michael acceptor, then added in the acid to protonate, and that gives us the 1,5-dicarbonyl. Now, you don't necessarily have to use LDA for this. It just makes it a little bit cleaner to use that. You can do a Michael reaction like this. Now in this case here, there's multiple enolizable protons there. All of those are analyzable protons. But the one that becomes a nucleophile is this one right here, because that's the most acidic one. And there's the resulting product, a 1,5-dicarbonyl. Okay. Now, what makes a Michael acceptor is it's an alkene attached to an electron withdrawing group. Why that's important is here, this Michael acceptor right here is called methyl vinyl ketone. Or MVK for short. And you can think of it as having these resonance structures. The carbonyl as an electron withdrawing group, what that's able to do is pull electrons away from that alkene to put an electrophilic site at the end. And that's the site where nucleophiles attack. So what the electron withdrawing group does is it creates a delta positive at the end, and that's where nucleophiles attack. And the more electron withdrawing groups attached on the other side, the more likely they'll attack. In fact, there's quite a few molecules out there that are very potent Michael acceptors. This molecule right here is called CS gas. It's what's used in tear gas. And the way it works is you have two electron withdrawing groups. They're both pulling electrons away from this carbon here. And nucleophiles reversibly add to that carbon. And those nucleophiles they can go up to either electron withdrawing group, and it's a reversible process. And a nucleophile just happens to be the tear ducts around your eyes. And that creates the burning sensation of tear gas, causing them to generate quite a bit of mucus in response, as well as tears, and that makes everything quite uncomfortable. And so, after a while, though, it is a reversible reaction. The nucleophile is kicked off, and as a result, the tear gas loses its effect after a while. Another application is crazy glue. A lot of crazy glue or super glues consist of what are called cyanoacrylates. what happens here is your nucleophile on one of your molecules adds in, and one of the things that you're gluing together adds into this as a Michael reaction. Now this right here is an enolate. That enolate reacts with another molecule, the ethyl cyanoacrylate. Creates another enolate. That enolate reacts again and again and again, and you get this polymer between the two surfaces. Eventually, this nucleophile reacts with an electrophile on the other surface, and you end up linking the two together by a covalent bond. And this reaction is a very, very fast reaction. Surgical glues and surgical adhesives. They're very similar to crazy glue. The only difference is, oftentimes instead of using ethyl groups on the esters, they use octyl or hexyl groups on there, or sometimes butyl groups on there. And it doesn't affect the reactivity that much, except it slows it down a bit. Because this first reaction is highly exothermic, and it generates a lot of heat. By having the longer chain there, that slows down the reaction, probably because not all of them can fit together right away and react right away. And so it slows down the reaction, lowering the amount of heat produced, so therefore the reaction doesn't heat up quite as much, making it a little bit better for biological systems, so it doesn't increase inflammation. Now, you might wonder, why don't the nucleophiles attack the carbonyl carbon? And the answer is, they can, and they do. Typically, though, weak bases do conjugate addition. What I mean by conjugate addition is instead of adding at carbon 2, they add at carbon 4. So to kind of give an idea of that, why weak bases have a tendency to add to carbon 4 instead of carbon 2, let's talk about cyanide. And due to the carbonyl being electron-withdrawing, that's probably the most reactive site. thing is, though, this reaction is completely reversible. Then the cyanide adds. In the conjugate fashion. This reaction is also reversible, but not as much. If you have a proton source present, we'll just say there's water present, protonate pad. Okay, we have two types of products here. This one is the one that's formed the fastest. This one, on the other hand, is a tendency to be much more stable. And that's the thermodynamic. With all the steps being reversible, the major product that you get is a thermodynamic product. The reason for this here's the kinetic product, because that's the one with the lowest barrier to it. Here's the thermodynamic product. That's the one that's the most stable. Now, in an irreversible reaction, the major product is kinetic. In a reversible reaction, the major product is the thermodynamic product. And the reason why the major product is the thermodynamic product is in the case of a kinetic product, you only have two rates to worry about. These two. And this is faster, because it's low in energy. But when you're dealing with the thermodynamic product, you have two additional rates to worry about. And so when it's reversible like this, yes, a majority of it first goes to the kinetic, but that's also the most likely one to go backwards. And then go the correct way to get to the thermodynamic. The thermodynamic product, going backwards, has the largest barrier to that. Because that has the largest barrier, that's the least likely one to occur, and so you just get this gradual accumulation of the thermodynamic product, the more stable product. Now, the less basic your nucleophile is, that increases the chances of this being completely reversible, increasing the chances it's actually thermodynamically driven as opposed to kinetically driven. Now, there is an exception to this, but that exception we'll cover next week, of a case of a very strong, irreversible one that gives the thermodynamic product, but that one will be addressed next week. But for the most part, your products are going to be thermodynamic. And when we're talking about strong bases, which ones go thermodynamic, they have a tendency to be pKa's, conjugate pKa's, less than or equal to 25 or so. So enolates and below. And the weaker the base, the more likely it's to go to this. Okay. Now, and sometimes some reactions can end up going a bit further than you expected. Like, take a look at this compound here. You take this molecule and react it with methyl vinyl ketone and base and a proton source. You have a Michael acceptor and have this. Thing is, though, you don't end up with a 1,5-dicarbonyl. The major product of this reaction happens to be this. And this reaction right here is a Robinson annulation. And this may look like a complex reaction, but we've done this mechanism before. And if you're trying to figure out what the mechanism is, for that, I suggest that you break down the product. 1, 2, 3. That's as a alpha beta unsaturated double bond. It has a 2,3 double bond. That's a product of an aldol reaction. For the aldol breakdown, we break the 2,3 bond. Carbon 2 gets an H. Carbon 3 gets a carbonyl. And then if we number these again, 1, 2, 3, 4, 5, that's a Michael. If we break that down, so carbon 2 gets an H, 3 and 4 gets a pi bond. Whoa! 5 bond to carbon. Gotta watch out for those. You can't just start your numbering when you're dealing with Michael at any carbonyl can be 1. You have to make sure that carbon 4 has an H. And in this case, carbon 4 doesn't have an H. But if we number it the opposite way, so that's a 1,5-dicarbonyl, that's a Michael. And in that, we break the 2,3 bond. Carbon 2 gets an H. Carbon 3 and 4 get a pi bond. We could break this down even further, but there's no need, because we're at our 2 starting materials. Now, you can use this breakdown to figure out the mechanism. The mechanism of the Robinson annulation, all it is a Michael addition followed by an aldol condensation. So the mechanism. The first step in the mechanism so far has been formed a nucleophile by deprotonating. We know which carbon we want to deprotonate because that's always carbon 2. And so when we map the numbers back, over here, carbon 2 is this carbon here. So that's the hydrogen we pull off in the mechanism. And once you formed your enolate, then you bring in your electrophile. Your electrophile has carbon 3 on it. Followed by protonation of the enolate, give you the 1,5-dicarbonyl. So we have done the Michael addition and completed that. Now we need to do the aldol condensation. We can refer back to our breakdowns. And what I'm going to do is I'm going to erase these numbers here. And I'm going to copy the numbers from the aldol breakdown on this. 1, 2, 3. These numbers are from this. The hydrogen we want to take off to go backwards is this hydrogen right here. That hydrogen is here at the end. I'm going to use a base. If you use hydroxide, that's fine. I'm using ethoxide because we just generated it up here. Either one. Form the enolate. I'm just going to redraw this in a different conformation. And from the above one, there is the carbons. We form the enolate, and we use that to attack the electrophile. And then we protonate. And that's the aldol reaction. Now we just need to do the condensation, the elimination portion, to get rid of the OH. Now, I know it's tempting to do this. Don't. To form the elimination product, it's not an E2 reaction. OHs are terrible leaving groups in E2 reactions. You can't use an OH as a leaving group in an E2 reaction. Instead, it goes through the E1CB reaction, where you take the proton off first. And you do this because that's an unusually acidic proton due to the presence of the carbonyl. Think of it as just forming an enolate. Once you have that enolate, then the leaving group is kicked off. And together, by doing the Michael followed by the aldol, together that gives you the Robinson annulation. And what to look out for the Robinson annulation is always this pattern, a cyclohexanol. Okay. All right. Last reaction I want to talk about today is the Mannich reaction. Or sometimes it's pronounced the Mannich reaction. It's very similar to the reactions that we have been doing before. Except the iminium is the electrophile. Basically, a Mannich typically consists of a ketone, an amine, and an aldehyde in weakly acidic conditions. To give a 3-amino carbonyl. Now, very similar to the aldol reaction, here we have 2 new chiral centers, and so you'll get a mixture of stereoisomers, diastereomers, and enantiomers. But we're not going to worry about the stereochemistry of this reaction. With that said, this reaction is very similar to an aldol reaction, except you have an initial step of forming the iminium. And so what happens in this reaction is the amine, the aldehyde, under the acidic conditions, react first. To form the iminium. This is the electrophile. The nucleophile then comes in, and the nucleophile, we've been using enolates in the past, though chances are, under these weakly acidic conditions, or weakly basic conditions, the nucleophile is actually an enol. Or if you show it as an enolate reaction, I'm okay with that as well. Just because we're not in strong acid or strong base conditions. Strong acid conditions, your nucleophile will be the enol. Strong base conditions, your nucleophile will be the enolate. In the reactions we've covered previously, we've been doing them under strongly basic conditions, so we've been focused on the enolate. Here, since we're neither in a strongly acidic or strongly basic environment, you can use either one. So let's go ahead and draw the mechanism of this particular reaction. If I can, sorry. Okay. So the mechanism of the reaction. Drop the starting materials. First thing to do is use those to form the electrophile. To do that, we do amine formation. In amine formation, the nitrogen attacks the aldehyde because the aldehyde is more electrophilic than the ketone is. And also the nitrogen is a basic nucleophile. Basic nucleophiles attack carbonyls unaided. There's no need to protonate it first. And afterwards, you can protonate it. Now, if you use the protonated amine as a proton source, that's perfectly acceptable. If you use the deprotonated acid as the base to deprotonate this nitrogen, that's perfectly acceptable. What I don't want to see is this. This is not acceptable because of the strained force-centered transition state. Don't do that. You got to do one at a time. Doesn't matter which one you do first. Protonate or deprotonate first, and then protonate or deprotonate the other. But you have to do it one at a time. Don't do them simultaneously. Then you have the hemiaminal. This is an unstable compound because it has an OH attached to the same sp3 carbon as a nitrogen. These cannot be isolated. Very, very reactive. They either go backwards or they go forwards to form the imine. Then nitrogen swings its electrons down, kicks off. Water is a good leaving group. And then we have the aminium which is the electrophile. Now, once we have our electrophile, we need to also make our nucleophile. Now, I said the nucleophile could be an enol or an enolate. To make the enolate, you basically just deprotonate. To make the enol, what we do is we protonate first. Followed by deprotonation. And then we have our nucleophile. And once we have our nucleophile, we bring in our electrophile. Electrons from the O swing down, kick these electrons over to here, kicks the electrons up to the nitrogen. Followed by deprotonation. Now that could be the conjugate base of acetic acid. It can be a lot of different things. I just chose the neutral amine. And that gives our product there. And this is the Mannich mechanism, or the Mannich mechanism. Now the Mannich breakdown. For the breakdown of the Mannich, the pattern to look for is a 3-amino carbonyl. And so if we number 1 at the carbonyl, 2, 3, or we can number the other way, 1, 2, 3, we have two options there. Turns out the red is correct. We only number the carbons. This, let me draw this in blue. This is a 2-amino carbonyl. It's not a 3-amino carbonyl. So you have to watch out for that. A 3-amino carbonyl has a nitrogen attached to carbon 3. And so the way you break it down, and this is the most complicated of the breakdowns, you break the 2,3 bond. And the N3 bond. carbon 2 and the nitrogen get a hydrogen. Now, before, we haven't had to draw in any hydrogens when it comes to this step. Now, we do, because it's a nitrogen. You should always draw in any hydrogens that you draw the label for. What I mean by that is, you don't have to draw in hydrogens attached to carbons, but you do need to draw in hydrogens attached to any other atom. If you ever draw in the carbon as a C, then you need to draw in the H's to that C. But I digress. Remember this step right here. And last thing, carbon 3 becomes a carbonyl. Carbon 3 right here gets a double bond O. Now, if you drew this, that's incorrect, because I've drawn in the C. Once I draw in the C, I have to draw in all the hydrogens attached to it. In this case, there are 2 hydrogens attached to it, so I would have to draw that in. These 2 things are equivalent, but it is not equivalent to that. Three minutes left. On Monday, we're going to be talking about a new set of reactions called Umpolung. And to sort of give you some practice on this, we'll do some breakdowns of these. So I'm going to go ahead and give you the last 2 breakdowns we have. And they are called Umpolung breakdowns. And where they come from, the patterns are 2 hydroxy carbonyls, and 1,4 dicarbonyls. These are the last 2 breakdowns we have, and both of these are Umpolung. In the case of the 2 hydroxycarbonyls, you break the 1,2 bond. This is different from all the other breakdowns we've done. You break the 1,2 bond. Carbon 1 gets a hydrogen. Carbon 2 becomes a carbonyl. Like so. Now for the 1,4 dicarbonyl, the Umpolung breakdown is you break the 1,2 bond. Carbon 1 gets the hydrogen. Carbon 2 and carbon 3, they get a pi bond. Now, since it's a 1,4-dicarbonyl, we could have numbered it the other way. Okay, so if you break the one-two bond, in this case this is carbon 1, that gets the hydrogen. Carbon 2 and 3 get the pi bond. Either of those ways are acceptable. Now, these breakdowns are pretty straightforward, but they're going to help you a lot in these mechanisms and in these synthesis problems. And so what I'll do is, under exam 3 practice, is post a PowerPoint with all 5 of these breakdowns on there and have you predict the products, or sorry, predict the starting materials on these. So that will be available on Canvas. Okay, have a great weekend, and well, we'll talk to you later.